It is 8:47 a.m. on a Friday, and a university department faces an administrative deadline. By the end of the day, they must submit documented fairness audits for their course assessments, or forfeit their eligibility for a $2.4 million program accreditation. That budget hangs entirely on reaching an agreement over a single Python grading rubric. The human committee assigned to the task is deadlocked. A pedagogy specialist wants 40% of the grade anchored to algorithmic strategy. A domain expert insists edge cases should dictate half the score, and an assessment designer argues that any criteria that are not rigid and binary will fail an inter-rater reliability audit. You have 3 qualified experts. Handing this prompt to a single state-of-the-art large language model yields a fast result. It will generate a readable, formatted rubric. It will also likely ignore the vital edge cases and partial credit mechanics that the human experts were fighting intensely over. Generating text is straightforward. The engineering challenge is aggregating competing, specialized philosophies into a cohesive system without letting a single perspective dominate the final output. If you drop multiple identical models into a naive chat interface and ask them to collaborate, they do not debate. They exhibit correlated error groupthink. The models will often agree with the first suggested output and amplify the same shared mistakes. Agreement in open chat is mechanically simple. This tree maps the evolution of multi-agent systems. Agent 29 integrates earlier orchestrator debate structures and verifiable logic paths from the explainable agent. For this crisis, we apply this architecture to the leaf node, multi-agent rubric design with collaborative consensus. The operational philosophy here is strictly defined. This system is designed as an adversarial jury, not a single monolithic reasoner. True collective intelligence relies on engineered disagreement. A committee of agents reaching consensus too quickly is often a sign the system is reflecting baseline assumptions rather than testing them. This flowchart tracks the agent's explicit execution layer on LangGraph. Phase 1 starts with independent proposals. The primary constraint is absolute sequestering. Pedagogy, domain, and assessment agents receive the problem, but their initial drafting is node-locked. They cannot see each other's work. If agents peek at competing proposals, early anchor bias takes over. Operating in isolation, the agents return divergent drafts. Receiving 3 incompatible first drafts is the metric that indicates the independence architecture is functioning as designed. There is a hidden mechanical threat in Phase 1. If all 3 of these agents run on the same backend LLM, they are pulling from the same training data and inductive biases. This creates a risk of correlated error groupthink. The first programmatic defense against this is role mapping. We apply distinct system prompts to force each instance into a rigid perspective. One evaluates purely on cognitive load theory. Another scans exclusively for PEP 8 code style and algorithm correctness. The second defense is mathematical. We inject a random temperature perturbation of plus or minus 0.1 into each node during generation. This variance ensures the same neural pathways aren't activated simultaneously across all agents. The third layer is a strict 500 token output cap. This prevents agent collapse, a failure mode where one reasoner dominates the context window simply by being the most verbose. Finally, we implement a fallback trigger. If the main agents unexpectedly align on a flawed meta rule, like deciding all criteria must be binary, thereby removing partial credit, the system injects a low-weight random agent. This agent proposes a completely different framework to break the premature agreement. When deploying multiple agents on a single LLM foundation, moving into Phase 2, the system transitions to the devil's advocate critique. We now have 3 isolated, divergent drafts that must be combined without letting one override the others. We handle this using a rotating adversarial manager via LangGraph's Send API. In each round, one agent is handed the red pen. It is forced by the system constraints to attack the competing proposals, and it is explicitly banned from defending its own. In round 1, the pedagogy agent critiques the domain expert. It points out that prioritizing edge cases ignores the student's process. A student could fail to merge the lists entirely, but still get half credit just for handling an empty list correctly. The assessment specialist then rotates into the critic role, flagging words like strategy and readability as subjective. If two teaching assistants define those terms differently, the rubric becomes difficult to defend during a grade appeal. This forced adversarial rotation prevents the groupthink from calcifying. In production benchmarks, forcing this mechanical disagreement drives a 12% jump in critical risk identification. This multi-agent design aligns with the requirements of the $25 billion EdTech AI market as of 2026. This market landscape tracks major frameworks in this space, separating general multi-agent systems from stateful orchestration like LangGraph. While chat frameworks suit prototyping, their conversational structure leads to token bleeding. Simultaneously, incumbents like Notion and Adobe are burying consensus loops into collaborative workspaces. The pressure forcing this architecture is regulatory. The EU AI Act classifies automated educational assessment tools as high-risk systems. This classification requires transparency regarding how a grade was determined. The platforms securing enterprise and state contracts are those embedding compliance mechanisms and explicit audit trails directly into their directed acyclic graphs. The adversarial loop needs a stopping condition. The rotation terminates when the statistical variance of the normalized rubric scores drops below a threshold of 0.05. Once the variance stabilizes, the graph advances to Phase 3, expertise-weighted voting and consensus synthesis. The surviving data points are merged using a linear opinion pool. The final rubric is a mathematical blend of the agent scores, rather than a majority vote. The system does not weigh every agent equally. A Bayesian logistic regression adjusts each agent's voting power based on historical calibration accuracy from past audits. By default, Pedagogy carries a 0.35 weight, the domain expert 0.40, and assessment 0.25. Finally, the synthesizer agent runs a clustering algorithm on the criterion embeddings. This targets and merges any redundant line items, delivering exactly 7 clearly defined evaluation criteria. The resulting rubric is a hybrid that no single agent proposed at the start. It is the specific logic that survived both the adversarial rounds and the clustering filter. This dashboard tracks the field NCACT metrics generated when deploying this architecture in a production environment. When this protocol was benchmarked against the historical performance of faculty-led committees, the results showed a significant shift. Human-designed rubrics for these courses historically achieved a 68% first-pass yield on accreditation audits. The consensus engine raised that figure to 92%, largely by prioritizing the edge cases that human committees often overlook. The system generates more than the rubric itself. It produces a cryptographic audit trail documenting every rejected alternative and the logic of the debate rounds. For the accreditation board, this documentation serves as proof of a rigorous, bias-tested process. The program's compliance is built on the mathematical record of how these fairness constraints were applied. Agent number 29 represents the structural inversion of earlier architectures. Instead of orchestrating agents to serve one individual learner, this system orchestrates specialized agents to produce one auditable truth. This concludes the scaling of digital consensus. The next evolution requires these digital logic systems to break out of the server environment. In our next profile, the agents stop debating on screens and start taking actions in the physical world. To study the complete LangGraph deployment code, including the specific temperature perturbation logic and the send API configuration, refer to the technical blueprints in 30 agents every AI engineer must build. In a high-stakes deployment, the most capable AI architectures do not seek immediate agreement. They are engineered to survive the friction of structured disagreement.